Namaste, welcome to the next video of Machine Learning Techniques course. In this video, we'll implement Softmax Regression from scratch. Softmax Regression is a classification method which generalizes logistic regression. It is used mainly for multi-class classification. The working of Softmax Regression is depicted in the following figure. For k class labels, the input feature vector goes through k different linear combinations, one per each class label. These k values are then passed through the softmax activation, which returns a probability vector containing k components. The ith component denotes probability of an input belonging to class label I. The softmax regression is trained with categorical cross entropy loss, which is computed based on the actual labels and the predicted labels. Note that the labels are represented in one-hot encoding. So here you can see that this is the input feature vector which has got m features. Here we denote the total number of classes by C. So there are C such kind of linear combination units. So each feature goes through each of these C linear combination units. So in that sense, there are C linear combinations that are happening, and every feature participates in these C linear combinations. Then these linear combinations are used inside the softmax activation, which gives us C different values which are probabilities of an example belonging to the respective class label. Just like any other machine learning model, we'll list down 5 different components of softmax regression classifier, and these 5 components you already know about them, which are training data, model, loss function, optimization procedure, and model evaluation. We'll import useful libraries like NumPy, then keras.dataset. From keras.dataset module we import mnest, and then for plotting we import matplotlib.pyplot. The training data contains feature matrix and label, and here the label is actually the multi-class label. So there are more than 2 classes. So this is one of the k labels that we will be having for each example. For the purpose of this illustration, we will be using mnest handwritten digit dataset. You are well familiar with mnest handwritten digit dataset in machine learning practices course. Those who are not taking the practices course, mnest handwritten digit dataset contains 28 cross 28 images. So each input is in form of 28 cross 28 image of a single handwritten digit, and each image is labeled with the digit present in it. So there are 10 digits, hence there are 10 classes, 0, 1, 2, all the way up to 9. So here we load mnest dataset with mnest API from Keras, and we call mnest.load_data that gives us training feature matrix, training labels, test feature matrix, and test labels. There are 60,000 examples in training and 10,000 examples in the test. And here are some of the data samples. So this is an image of handwritten 5, and you can see that the label for this image is 5. Then this is the image of digit 0 and label is 0, and so on. So these are our input images, and this is the label that we would like to predict for such an image. So each image is a grayscale image with size 28 cross 28. So as a first step, we flatten each input image into a vector of length 784. This 784 is indeed equal to 28 cross 28, and these 784 numbers represent intensity at each pixel in an image. So we reshape the training feature matrix and the test feature matrix. Each pixel takes a value between 0 and 255. We scale each value by dividing it with 255. For a softmax regression, the label vector y needs to be in one-hot encoding format. So we write a small function that takes the label vector y as an input and returns one-hot encoding vector. Let's look at the model of softmax regression. So we have already seen this. So there are m input feature, they go through C linear combinations, and then there is a softmax activation. For each class, let's say Z1, we compute the probability of an example belonging to Z1 using softmax activation, which is computed as exponential of Z1 divided by sum of exponential of Zi, I running from 1 to C. So you can see that in order to compute this probability, we are not only using the corresponding activation, but in the denominator we are using all activations. All C activations are being used in the denominator. So there are two stages. First is a linear combination, which is this particular stage, followed by softmax nonlinear transformation. So linear combination can be represented in vectorized form as Z is equal to x times W plus B, and B is the bias. So for n given examples with this vectorized form, we can calculate the linear combination in one shot. And once we obtain this Z, we apply softmax nonlinear transformation on this Z by calculating the ratio of exponential of Z divided by sum of exponential of Z. Here we perform this sum row-wise or by every example. So softmax classifier provides a probability of an example belonging to a class. For example, probability of y equal to q, or the example belonging to class q, parameterized by weight matrix W and weight vector B, is equal to exponential of zq divided by sum of exponential of zk, k running from 1 to k is the total number of classes. Let us implement softmax regression. So the vectorized form can be implemented simply as z equal to x times w plus b. Each class has m plus 1 parameter, that is 1 bias, and m weights corresponding to m features. So we have a linear combination function that takes feature matrix as an input and the weights w and b as input, and it calculates x times w plus b, and it returns the linear combination. In the second step, we calculate softmax for each class using the formula that is given over here. And the class label with the highest value of softmax is assigned to that sample. So every class has a different set of weights and biases that you must have noticed over here. Every class has its own set of weights and biases. So we compute the softmax given Z that we obtained from linear combination. So here what we do is we actually have one more step before actually applying softmax. We subtract the max value of z for the numerical stability, and then we perform the softmax computation, which is exponential of I divided by sum of exponential of I, and we return the softmax activation from this function. So this was about model. The next step is the loss function, and here we are using categorical cross entropy loss as a loss function. For any pair of label vector yk and a model prediction yk hat over k classes, the loss function j is given as the loss function is parameterized by the weight vector w and b, which is the bias vector. It is equal to negative of sum over all classes k yk times log of yk hat. So this yk hat is the prediction and this yk is the actual label. Now the next step is to perform an optimization procedure to estimate the weight matrix W and bias vector B by optimizing the loss, which is J of W comma B. So there are m times k entries in weight matrix W and k entries in bias vector B. We said that every class has its own set of weights and bias. Now we are going to calculate a partial derivative of loss function with respect to weight and bias unit. So let's say Wj comma I represents weight for jth feature in ith linear combination. So we will be calculating partial derivative of the loss function with respect to W of j comma 1. So think of W is a matrix and j comma I represent the entry on jth row and ith column. And B is a vector, so B of I represent bias for ith linear combination, and we also calculate partial derivative of loss with respect to Bi. Now this loss combination is not as straightforward as we were doing in earlier machine learning methods, and the reason for that is in this network structure. So remember, for calculating the probability for every class, we are not only using the linear combination of that class, but we are also using linear combinations from all other classes. And weights are present over here. And the loss is calculated from all these values that we are getting from the softmax activation. Now this particular loss is related to weights through a maze of computation. So this loss first depends on the value of the predicted label, and this predicted label in turn depends on bunch of activations, in fact all k activations, and these activation in turns depend on the weights that we select. So in order to calculate the partial derivative of the loss with respect to weight, we'll have to calculate partial derivative of loss with respect to the predicted output. Then this predicted output has to be differentiated with respect to all the linear combinations, and then these linear combinations will have to be differentiated with respect to the weights. So this is some kind of a chain of derivatives that we are using here. So what we'll do is we'll use what is called a chain rule of derivative in this particular case. So this will be very common when you learn neural network models, or more specifically, in modern days they are called as deep learning models, where you will see some such kind of situation where weights are not directly connected to the loss calculation, and then we'll have to do some such kind of operations using chain rule of derivative, and we'll see how to represent this. Now we are explicitly writing this, so Zi is calculated as Bi plus x1 w of 1 comma I plus x2 w of 2 comma I all the way up to xm w of m comma I. So we can write this compactly as b of I plus sum over all m feature xj w of j comma I. And Zi is used for softmax calculation in the numerator for ith class and in the denominators of all the classes. So softmax of Zi is calculated as the ratio of exponential of Zi divided by the exponential of Z I comma k across all k classes. And we have already talked about this. Loss is computed based on the output of the softmax, hence loss and weights are not directly connected. They are related through first the prediction and then through Z. So what we'll do is we'll first try to calculate, use the chain rule of derivative in the following manner. So we first in order to calculate the partial derivative of loss with respect to weight matrix, we'll first calculate partial derivative of loss with respect to the linear combination, and then the partial derivative of linear combination with respect to the weight. So here we are calculating the partial derivative with respect to w j comma I, which is one single weight in the weight matrix. And here we first differentiate the loss with respect to the linear combination for ith class, and then the linear combination for the ith class is differentiated with respect to the weight, which is w j comma I, and you can see that this w j comma I is used in the calculation of Zi over here. So it makes sense to differentiate this Zi with respect to this particular weight. In the same manner, the bias, so the partial derivative of the loss with respect to bias I, we first calculate the partial derivative of loss with respect to Zi, and then the partial derivative of Zi with respect to Bi. So we need to now compute three partial derivatives, this one, and this one. So which we have written here: partial derivative of loss with respect to Zi, partial derivative of Zi with respect to w j comma I, and partial derivative of Zi with respect to Bi. We will calculate them one by one. First we calculate the simpler derivatives, which are derivative of Zi with respect to w j comma I, and we know the formula for Zi, which we substitute over here. So this is the partial derivative of Bi plus summation of xj into wji, j running from 1 to m, and with respect to w j comma I. When we perform the derivative of this equation with respect to w j comma I, what we get is the first derivative of Bi with respect to w j comma I will be 0, and for this term we'll essentially get xj. In the same way, we calculate partial derivative of Zi with respect to Bi. We again substitute the formula for Zi, and here the partial derivative of the second term with respect to Bi will be 0, and for the first term the derivative is 1. Now comes the fun part where we calculate partial derivative of the loss with respect to Zi. Now note that Z is related to the loss through the prediction y hat. So we'll be using chain rule one more time. And moreover, Zi is also used in calculation of yj where j is not equal to I. Hence we need to make use of an addition. So the partial derivative of the loss with respect to Zi is equal to the partial derivative of loss with respect to the prediction for ith class, and then the partial derivative of the prediction for ith class with respect to Zi. So this happens for ith class, and then for all other classes that are not equal to I, we have partial derivative of the loss with respect to the prediction for class J where J is not equal to I, and then the partial derivative of prediction for class J with respect to Zi. Now let's calculate the partial derivative of the prediction for ith class with respect to Zi. Let's substitute the formula for the prediction, which is the softmax activation. So we get partial derivative of the softmax activation with respect to Zi, and for this we use quotient rule of derivative. And in the quotient rule, the denominator, we take the square of the denominator, and then we have the denominator into partial derivative of the numerator minus the numerator into the partial derivative of the denominator. So you can see that the partial derivative of e raised to zi with respect to zi is e raised to zi, and then we copy the summation term as it is, and here we copy this particular term as it is, and the partial derivative of the sum of exponential of zk over all k classes with respect to zi is nothing but exponential of zi or e raised to zi. So now we can simplify this with algebraic manipulation. All that we do is we separate these two terms in the numerator, and then what happens is this particular one of the summation gets cancelled, so we get exponential of zi divided by the sum of exponential of zk over all k classes minus exponential of zi divided by sum of exponential of zk over all k classes whole square. So this is nothing but yi hat, and this is yi hat square. So we get the partial derivative as yi hat minus yi hat square. Now we will calculate partial derivative of the prediction for jth class with respect to zi. So we again substitute the softmax activation for class J and differentiate it with Zi. So again, using the quotient rule of derivative, we have square of denominator in the denominator, and then we have denominator into partial derivative of the numerator minus numerator into the partial derivative of the denominator. Now here the partial derivative of exponential of zj with respect to zi is 0, and the partial derivative of this summation is exponential of zi. So this term becomes effectively 0, so we have minus exponential of zj into exponential of zi divided by the square of sum of exponential of zk sum over all k. So we'll simplify this and write these two terms separately. So we have the prediction for jth class into prediction for ith class. So this is negative of y hat j into y hat I. Now we will substitute all these intermediate calculations into this particular formula. And we get minus yi by yi hat into yi hat into 1 minus yi hat plus sum over all j's not equal to I minus yj divided by yj hat into minus yj hat into yi hat. So now we can do simple algebraic manipulation. So these two yi hats will be cancelled and this will be minus yi plus yi into yi hat. So this yi is multiplied inside this particular bracket. So we get minus yi plus yi into yi hat plus, so basically these two yj's, yj hat will cancel, this minus minus will become plus and we get yj into yi hat. And now these two terms, if we combine these two terms, we are basically summing over all j's. This is j not equal to I and this is basically j equal to I. So we are summing up over all j's. So this is minus yi plus sum over all classes j yj into yi hat. So we are taking this particular the second term in the place of the first term and the first term is copied in the place of the second term. So we have yi hat into sum over all j's yj minus yi, and you know that sum of yj's over all j's over all classes is equal to 1. So this will effectively become yi hat minus yi. So now the partial derivative of the loss with respect to the weight, which is w j comma I, is xj into yi hat minus yi. Now let's write the partial derivative calculation in vectorized form. So partial derivative of the loss with respect to the weight matrix is the transpose of the feature matrix into the prediction matrix y hat minus the label matrix y, and the partial derivative of the loss with respect to the bias vector is simply the difference between the prediction and the actual labels. So we get the weight update rule. So the weight for the next iteration is updated with the current weight minus alpha times the partial derivative of loss with respect to the weight, and the bias is updated with the current value of bias minus alpha times the partial derivative of the loss with respect to the bias vector. So with these update rules, we can use gradient descent to find the optimal values of the weight matrix and the bias vector. We implement the fit function that takes the feature matrix, label vector, learning rate, the number of classes and number of iterations as input. And this is where the training loop is implemented. We first perform the linear combination followed by softmax activation. Then we convert our label vector into one hot encoding, and then we calculate the losses with respect to w and b. So here we have made one small change than what we have seen in the derivation. We simply multiply the partial derivatives by 1 over n, where n is the total number of examples, and then we update the parameters according to the update rule that we have seen. We calculate W as the current value of W minus learning rate times the gradient of the loss with respect to W, and B is updated to B minus learning rate times the gradient of loss with respect to B. Then we calculate loss and append it to the list so that we can plot the learning curve later. The prediction is straightforward. We perform the linear combination followed by softmax nonlinear activation, and then we return the class with the highest value of the softmax activation. Now that we have implemented different functions in softmax regression, we'll use it to train a digit recognizer on MNIST dataset. So we call the fit function with the feature matrix from MNIST and the label vector with learning rate set to 0.9, number of classes equal to 10, and we train the model for 100 epochs. You can see that the losses are going down with every epoch. So here we are printing the losses every 10th epoch, and you can see that there is a downward trajectory of the loss. We plot the learning curve where we have number of epochs on the x-axis and loss on the y-axis, and this learning curve is kind of a sign of the classifier getting trained properly. The loss reduces after every epoch, which is a sign that the classifier is learning with every iteration. And we get the accuracy of 87.7% on the MNIST dataset. Maybe you can train it longer in order to get more accuracy. On the test set, we have slightly higher performance, which is 88.16%. And this is the confusion matrix for the test set, and we calculate the classification report on the test predictions. So we are doing very well on certain classes like digit 0, digit 1, digit 6. We are above 90%, and for some of the classes like 5 and 8, our accuracies or our F1 scores are not as good as some other digits like 0, 1 and 6. The overall accuracy is 88%, and we also calculate micro and macro average precision recall and F1 score. The micro average precision score is 88.16%, whereas macro average precision is 87.98%, which is close to 88%. We have plotted few predictions for your information. So this digit, the label is 7, and we also predicted it to 7. This is digit 2, which is correctly predicted as 2. So here there is one misclassification where this is actually digit 4, but we have misclassified it to digit 0. In this video, we implemented Softmax regression, and we also learned different components of Softmax regression model. We had a detailed derivation of the partial derivative of loss with respect to weight. We have tried to simplify it so that it is accessible to all of you. We also demonstrated the usage of Softmax regression implementation in recognizing digits on the MNIST dataset.